Hey guys, there's another question from section 5.4. This is number 209. Again, same question. We're asked to see if this limit converges, if the series converges or diverges by applying the limit comparison test. So our series is sum n equals to 1 to infinity of ln, natural log of 1 plus 1 over n, all over n. Okay, so we're going to compare this again to a series that we know for sure converges, or for that matter diverges. So I'm thinking of 1 over n squared here. Again, by the way, if you do compare to something that, a series that you think may work, and if it doesn't work, of course, you can always go back and check or change your p series. Okay, so now, obviously if it works, then you're done, but if it doesn't, there are other choices, okay? So I'm gonna go ahead and again look at the limit as n approaches infinity of our series, ln of 1 plus 1 over n, all over n, and then all over 1 over n squared. Now, if we do get a limit here, or we get 0 here, then by either part 1 or part 3, I believe, we do have a convergence of our series, because we know that p series 1 over n squared converges, okay? So again, as you do your little algebra here, clean this up, so you do get, this becomes the limit as n goes to infinity. So as you reciprocate the bottom times the top, you should basically end up with n times ln of 1 plus 1 over n. Okay? So obviously we can't apply the L'Hopital now, because this is infinity times infinity here basically. Or I should say 0 times infinity, because as n goes to infinity, but that of course becomes natural log of 1. So we're going to rewrite, I'm sure you remember from calculus 1, these are called indeterminate forms. We're going to rewrite this so we do get the form 0 over 0, so then we can apply L'Hopital. So I'm just going to rewrite, do a little algebraic trick here. So this same exact expression can be rewritten as ln of 1 plus 1 over n, and then instead of times n, over 1 over n. Because as you know, as you reciprocate the bottom, that just becomes n. So it does give you the same quantity, it's just that now we can apply L'Hopital, because now as n goes to infinity, of course, this becomes 0, natural log of 1 becomes 0, and also 1 over infinity becomes 0. So you do get 0 over 0. So now we can apply L'Hopital. So I'm going to do one more step here, and then I'll go move it upstairs. So this is the same thing as the limit as n goes to infinity. So derivative of the top, of course, is 1 over the function. Actually, let me just move this up a little bit. So derivative of top becomes 1 over the same function, which is 1 over 1 plus 1 over n, and then times the derivative of the function. Now, derivative of 1 is 0, and derivative of 1 over n, which is, of course, don't forget, 1 over n is the same thing as n to the negative 1. So as you apply the power rule, that should become negative n to the negative 2. The power negative. Let me again move this up a little bit so you can see it better. So again, derivative of natural log is 1 over the function, and then times derivative of the function. Of course, derivative of 1 is 0, and derivative of 1 over n, as you look at that as n to the negative 1, simply become negative n to the negative 2 by power. And also derivative of bottom is same thing, because again, derivative of 1 over n is negative n to the n times negative n of n to the negative 2, okay? So you can see now those cancel each other, because those are exactly the same expression. So as you can see, the negative n to the negative n, negative 2 cancels the negative n to the negative 2. So really all you're left with is a limit as n goes to infinity of 1 over 1 plus 1 over n. So obviously, as n goes to infinity, I'm going to go ahead and put it here. So as n goes to infinity, well, 1 over n goes to 0, and 1 over 1, of course, becomes 1. So that limit becomes 1. And so now we can say this series converges by, and this one is going to be part 1. So I'll let you go back and look in your book about the different parts of limit comparison test if you haven't learned them by now. So this will be by part 1 of, again, the limit comparison test, okay? So once again, we have a convergence series, because if you go back and look at the part 1, it says as long as you get a limit that is basically non-zero, and if the series you compare it to converges, so does your series, okay? Again, I'll let you go back and read comparison test a little bit more carefully. So this time we do get the limit of 1, which is of course positive, and obviously that means our series converges, okay? All right, guys, well, if you have any more questions, let me know, please.